Have you ever stopped to think about where the electricity that powers your life actually comes from? Well, today we're going on an incredible journey tracing the story of one of the most powerful and controversial elements on Earth, uranium. It's a story that literally begins in a dying star and ends with your light bulb.
I know, it sounds like something straight out of science fiction, doesn't it? But it is absolutely true. The element that can light up our cities was forged in the cosmos. And that's what makes it so fascinating. It has this profound dual nature. It can power our entire world, but at the same time, it holds the power to destroy it. So that leads to the big question, right? How do we actually make this stuff? Well, here's the twist. We don't. Humans can't create uranium. It's already here. The real story, the one we're diving into, is how we find this ancient element and then transform it from just a piece of rock into one of the most potent energy sources ever known. To understand this, our story can't begin on Earth. Nope, we have to go way back, billions of years ago, deep in the cosmos. This is Chapter 1, A Star's Legacy. That's right, uranium wasn't cooked up in some lab. It was literally forged in the unimaginable heat and pressure of a supernova. You know, a dying star's final, massive, explosive act. When our planet formed about 4.5 billion years ago, all that stardust, including uranium, got trapped inside its rocks. It's been hiding there, deep underground, ever since.
Okay, so let's bring it back from the cosmic scale right down to the human one. Because getting this stuff out of the ground requires a massive, massive effort. Why? Because it's found in such tiny concentrations. We're talking just a few hundred grams of uranium in an entire ton of rock.
So to get it, there are three main methods. You've got open pit mining, which is exactly what it sounds like. They carve these enormous pits right into the Earth's surface. Then there's underground mining, which means digging deep, hazardous tunnels. And then there's a more modern technique called in situ leaching, which is pretty clever. It basically dissolves the uranium right out of the rock while it's still underground. But there's a serious, invisible danger that comes with all this digging. While the uranium ore itself isn't intensely radioactive, the mining process releases radon, a really dangerous radioactive gas. It's a natural decay product of uranium, and because it's a gas, it can be inhaled, which poses a huge health risk to miners if there aren't extensive safety measures in place. All right, so once thousands of tons of that rock are pulled from the Earth, the next phase of the transformation begins. This is the journey from a simple stone into something called yellowcake. So at a processing plant, the ore goes through a pretty intense milling process. First, huge crushing machines break the big rocks down. Then they're ground into a really fine powder, almost like sand. After that, a chemical solution is used to leach out, or dissolve, just the uranium. Finally, that uranium is precipitated out of the solution into a solid form. And the result of all that work is a coarse, yellowish powder known as yellowcake. And despite the name, no, this has absolutely nothing to do with dessert. This is a concentrated uranium oxide, and it's the crucial raw material that's ready for the next and way more complex stage of refinement. But even as yellowcake, the uranium isn't ready for a reactor. Not even close. Its true power is still locked away, and unlocking it requires one of the most sophisticated and politically sensitive industrial processes on the entire planet. This chart shows you exactly why. You see, natural uranium is made up of two main types, or isotopes. Over 99% of it is uranium-238, which is pretty stable. The tiny sliver, just 0.7%, is uranium-235. That's the one we need. That's the isotope that can actually be split to release enormous amounts of energy. So how in the world do you separate them? Well, the key is an almost unnoticeable difference in weight. Uranium-235 is just slightly lighter than U-238. You'll also see it's described as fissile. That's just the scientific way of saying its atoms can be split apart, which is exactly what we need for energy. And that tiny, tiny difference in weight is everything. So first, the yellowcake is converted into a gas. This gas is then pumped into thousands of centrifuges, which spin at mind-boggling speeds. This incredible force pushes the heavier U-238 gas to the outside wall, while the slightly lighter U-235 gas collects near the center. This process has to be repeated over and over and over again to gradually increase the percentage of U-235. And this is where the concentration becomes absolutely critical. For a nuclear power plant, you only need to enrich the uranium to about 3 to 5% U-235. But to create a weapon, that concentration has to be pushed all the way to over 90%. This single process is the fine line between peaceful energy and a global threat. With our enriched uranium finally in hand, we reach the final part of its journey, actually creating electricity. But this process brings both immense energy and a profound responsibility. And to get a sense of the power we're talking about, just look at this. The enriched gas fuel is converted back into solid ceramic pellets. And just one of these tiny pellets, about the size of a gummy bear, packs the same energy as an entire ton of coal. It's just an astonishing amount of power. These pellets are loaded into fuel rods and placed in a reactor. Inside, a neutron strikes a U-235 atom, causing it to split in a process called fission. This releases a huge amount of heat and more neutrons, which go on to split other atoms, creating a controlled chain reaction. All that heat boils water, the steam spins a turbine, and just like that, we have electricity. But the story doesn't end there. After the fuel is used up, it becomes spent nuclear waste, and this stuff remains highly radioactive for thousands and thousands of years. Safely storing this material is the single biggest technical and ethical challenge of nuclear energy, a responsibility that lasts for generations to come. So, from the heart of a dead star all the way to the light bulb in your room, uranium's journey is a story of immense power and incredible human ingenuity. So, I'll leave you with this. As our world demands more and more carbon-free energy, is mastering the power of this ancient stardust our greatest challenge, or is it our greatest hope?